All right, we're up and running. Cool, welcome back. Hope everybody's doing well.
Oh no, but
No?
there's an associative arrays in C. I don't even know that.
There's a what?
Also called.
Associative arrays in C.
I
There's.
didn't know that there was associative arrays in C.
Well, the only version I know is a package called DBM, like database manager, and it's usually GDBM.
Sam mentioned that they are in C. I'm assuming. Did you mean the hash table or something, or? Oh, hashes. Yes.
Hashes in general. Yeah, it'll focus eventually.
Bugs in your hash table code.
You've been finding bugs in my hash table code. Cool. What kind of bugs?
Some problems with license plates over 30 characters. Some seg faulting with weird HTML stuff.
My code only works with 32 characters, including a null terminator.
Right. Yeah.
I bumped it up for the class because.
Parsing on dump integer.
Mm-hmm.
You can put stuff after the.
Yeah, it takes extra stuff after. Yeah, cool. Good finds. I should do that intentionally, actually. I should, like, post sample code and ask people to find problems with it. And then, like, give points for that. Because that would be a good way to practice, like, really, like, doing the final testing on code. Which people, you should do on your own code before you turn in. But that could be a good way to do some practice with that. I'll have to think about that. But yeah, nice job finding those.
Can you please go over how we implement the hashes again? Because I don't know what I'm supposed to do in hashing it. I don't know how I'm supposed.
Can you say that first part again? How we do the what?
Implementation of the hashes, i.e. and hashing it, and etc.
Yeah.
Like, is it a linked list implementation or something?
So the hash itself is an array, and we're calling this hash table. So here's just an array. I'll draw it horizontally for once. And it goes from 0 to a hash size -1. And each of these is a pointer to a sentinel node. And this might, point to null if there's nothing hashed in that index, and this might point to a really big linked list, and so on. So we've got an array of sentinel nodes. That's what the hash table is. It's an array of sentinel nodes. And so there's two main aspects to this. So what does our main program do? Process command line arguments to get the database name and the hash size. So they've got a specified database name on the command line, and that becomes, that's the first argument. And then if they specify a second argument, it's an integer, that's the hash size. Otherwise, the hash size is 100. So that's the first part. That's kind of a preamble. The second part is ingest the database file. All right, so So these are the main steps in your program, right? Three things. First is just processing the command line arguments. Second one is to ingest the database file. So how do we do this? Call hash init to create an empty, an array with sentinel nodes that are all pointing to empty lists. So that creates that initial empty data structure, and then open the database file, and then read a line from the database file, scanf it into plate, first name and last name, and then pass those to your hash add function to add them to the hash table, and go back up to the top, right? Until you run out of stuff to read from the database file. That's the whole ingest piece. And then the third part is user input. So read a line. If it's a dump command, I don't know if we have a hash dump function or if I made you spell that out. Let's see. So if it's a dump command, use hash dump. If they said dump a particular number, just call hash dump. If they said dump everything, then make a loop that calls hash dump for all of the entries in your hash table. If it's load, say again?
I had a question about that.
Okay.
So if it did, how would I know if it didn't enter a number? What would it just pass 0?
How do you know if the line you read has a number?
Yeah, because I'm about to work on my hash dump, but I'm not sure how to check on whether or not they enter a number in that function.
So hash dump has no knowledge of what the user entered. Hash dump is called with a hash table and a particular entry in the array that you want to dump. So this function has no knowledge of users or what the user typed or anything like that. But in your main program, when you read a line, you want to parse it, right? So first see if it's equal to exactly star dump. And if it is, make a for loop that dumps every cell. If it's equal to exactly star load, do what you have to do to dump out the load. Otherwise, try parsing it with scanf. See if it's star dump followed by an integer. And if it is, then go ahead and use that integer value as the argument to hash dump. And then if it's none of those things, it's a license plate to your license plate lookup.
Yeah, I see. I thought I'm doing both conditions in the same function.
Okay, no, the hash dump function is pretty basic.
Okay.
All right, so if it's a dump, use hash dump. If it's load, loop and call, and I think it's hash load. Actually, just call hash load. So if they say star load, you've already got a function to do that. Else, call hash find because they're asking for a license plate. So call hash find, pass it the hash table, the plate, and then 2 variables to hold the results if it finds the plate. And if it does, print out the values of those variables in the right format, and that's your output. And this just, goes back until end of file. So from the level of the main program, there's no funny business to do. There's very little involved with the hash, and there's nothing involved with the linked list. All right. The funny business starts to kick in when we look at things like the hash functions. But like hash add, all right, so we have to add a plate first name and last name to this hash table. You can do this in one statement if you want, but I'll break it out into a few statements. But this is really a one-line function if you put it all together. But if we break it into pieces, it grows to like 3 lines. So we can do something like this, you know, index equals hash plate. I'm doing pseudocode, so I'm not declaring my variable types. You know, this is an integer, so call your hash function, pass it the license plate, it'll give you back an integer. All right. Struct node star sentinel equals whatever is in that location in the hash table. Right, so this is an array of sentinel nodes. This is the location where the sentinel node for the list that this plate should go into. So you use that as an index in the table, you get back a sentinel node. And then you use that as the sentinel node to the list add function. That's your whole hash add function. Right, so this is what I mean when I say these are kind of wrappers around linked list functions. List add does all the actual work. It makes a node, it mallocs space for it, mallocs space for the fields, it copies the fields, it adjusts the next nodes so that it pushes this into the beginning of the list, and all of that good sort of stuff.
I have a question.
Okay.
So the which one was it? Hash load, right? Or no, hash dump.
Mm-hmm.
You send it the hash table,
Right.
and you send it the cell num, and that cell num is basically the index, right?
Mm-hmm. Exactly.
And then you just index the hash table and then run list print, correct?
Mm-hmm.
So basically, I added a thing in my hash dump where if I just send it -1, it just dumps everything, so then I don't have to loop in my main program.
Yeah, that's okay.
Is that fine?
Yeah, someone asked about that yesterday in class, and we talked about it a bit, and I said, yeah, that's fine.
Okay, cool. Yeah, because I didn't feel like doing anything with the hash table in the main program.
So that's a nice little trick that you can use to kind of embed multiple functions inside one function. And the caveat I made yesterday was be a little careful with that for a couple of reasons. Number one, if you had a teacher who was like super picky about, you know, following the specification, including, you know, saying if you add extra things, that's a no-no, right? You could lose points for that. Okay, I generally will not take off points if your function does more than what's required. But in some cases or in some job situations, right, you might really need to be able to follow this very, very precisely. And so that can be one detail. The second thing is those kinds of nice little tricks that save you some coding can grow to scary proportions after a set of code has been around for a few years. If lots of people are doing that and if other people are using those, whereas if you maybe made a hash dump all function, which is a totally separate function, and in that function you called hash dump in a loop, right? Well, now you can document that, you know, as a separate function. You can define the interface and so on. That's a little bit cleaner, and still saves you from having to, you know, make a loop inside your main program to dump all of the cells. So just some things to keep in mind. But yeah, for PA3, that's a fine thing to do. Yeah, yeah.
hash dump all or something.
But these are nice, and you know, especially if you're doing something like an embedded system where you don't have a lot of space, and things like that. There's little tricks like that you can do that will get you by in a pinch, and those are useful to know. So how do you code this in C, right? Well, coding the hash functions are you know, matters of basically calling the right list functions. And this, you know, if you add integer index struct node star sent, this is basically the C code, right? Add your semicolons at the end. This is basically the C code to do that. And then coding the list functions, that's, you know, where you have to actually get down and do the mallocs and the string copies and the string compares and all that kind of stuff. But that's you know, building on the linked list stuff that we've done in other assignments. So hopefully that helps. Implementing the hash, right? That's a for loop. So we've got our hash function. So, you know, set a variable sum equal to 0 for I equals 0, I less than string length plate I plus plus. Sum equals sum plus I times 1, I plus 1 times I plus 1 times plate bracket I. Close curly bracket at the end of your loop, sum equals sum percent hash table size, return sum.
Does that go in my hash add function? Because I wasn't sure whether to put that for loop for initializing the hash table like that.
So this, I would make a function called hash that takes a string, returns an integer, because you're going to use it multiple places. You're going to use it in hash add, you're going to use it in hash find. So make that a separate function. And then you can change it and tweak it and test it and all that good sort of stuff. Let's see. Yeah, go ahead.
So I'm confused. The assignment in for the startup, it implies that you need to have like some way of like limiting the size of the hash table.
Mm-hmm.
But
so you're looking at this second argument?
well, both, because the first one, like the first option has used the hash table of predefined size,
Mm-hmm.
one that is not defined by user.
Right.
And so I'm just wondering if like using like a counter integer variable to make sure that the hash table isn't too big would work.
So it's a little easier than that, actually, because you're creating the hash table in your code, right? So remember, in your hash init, you're going to do something like struct hash entry table, and you're going to allocate space for that. So size times size of struct, or just a hash entry, size of hash entry. So hash init, right? This function is called with a size argument, 100, 1,000, 5, however many spots you want in the hash table. And you actually create the hash table with that much space available. So it's not a question of limiting the table to that size. It's a question of creating the table with that size. And the size of the table is not, you know, how many things are in the table. The size of the table is basically how many linked lists we have. And the hash table is just a collection of linked lists. you know, we can have 1,000 license plates. We can store it in one linked list. We could store it in 10 linked lists. We could store it in 100 or 1,000 or 10,000 linked lists. So the size of the table, we're talking about how many linked lists are we using to store the information. And so we're not limiting how much information is stored. We're specifying how many linked lists do we have. So when you call hashInit size, you create an array with length size to store those linked lists. And then, you know, for I equals 0 to size -1, table bracket I equals list init. So now we go through and we create a new empty linked list in each of those, you know, 100,000 whatever locations in the array. And that's your hash table. It's this array of Sentinel nodes.
Okay. What's the for I parameters up there? I can't see them.
For I equals 0 to size -1. For each element in your array. So if your array is 100 elements, then you go from 0 through 99, and just set each of those to a new Sentinel node.
Okay.
And to get that Sentinel node, right, just call listinit. Let listinit do the heavy lifting of doing a malloc and, you know, put a magic field in the data value if you want, and so on and so forth. But from the code for hashInit, I'm just calling listinit, because that's what listinit does. It creates a new linked list, returns the Sentinel node. Let's see. So global variables, I don't know if the answer in chat answered the question, but, you know, in your hash.c function, that was probably really loud. In your hash.c file,
We have to have a hash.c file.
you don't have to, but I would recommend it because it will make things easier.
Would it be the same as like the function files in our other ones?
Yeah, you could make one big functions file with your hash and your linked list and your other stuff. That's okay.
I just left the names because then I'll have to change my make file.
Okay. Yeah, I mean, I'm not going to take off or award points based on how you break it into pieces. But it's a chance to, you know, get more practice with organizing things into separate files and, you know, adjusting the make file accordingly and so on and so forth. And definitely when you get to a university, I mean, you're going to be working on projects that are thousands of lines long, and you're going to have, you know, 10 or 15 page, you know, descriptions of the problem and lots of different parts and pieces, and being able to organize that is a huge part of these assignments, right? So if you can get, you know, any practice on that with you know, smaller assignments like these, I definitely recommend taking advantage of that. But yeah, okay, so I think that was already answered. But yeah, basically static int hash size, and then you can do, you know, hash init and put your function definitions in here and do your hash add and put your function definition in there and so on and so forth. And this thing, because it's declared outside of a function, is available inside any other function that's written below it in the file. And so that makes it global, but it's only global within this file. So you know, you don't want globals in your main program, but inside this package, which the user is never going to see the source code for, that's okay. It's not going to do any harm. And the user could even have, you know, a variable in their main program called hash size. It's not going to break anything. So that's fine. let's see. Do we have to assign a data value to each member of the hash table? So when you do your hash init and you malloc the space for this, that's when you want to go ahead and initialize each of these. And when you initialize, it becomes just a sentinel node, right? So this will be the address of a sentinel node, and that sentinel node has, 3 data fields: plate, first name, last name, and the next node. The important thing is the next node should be equal to null, and make sure you initialize that. Whether you put anything in the plate, first, last name fields of the linked list is up to you. It's totally your choice. But I can think of some things you could do in there that might make it easy. Like you could, store the index in the hash table as a string in the plate field of the sentinel node, or something like that. But there's no requirement for what you do with those data fields. All right, good questions, good comments. Any others?
It mentions in the assignment something about not holding a global in main of the hash size.
Right.
So I use the hash size in my main program.
That's fine.
Okay. I don't have the global in it. It's in my functions file.
That's perfect, yeah.
Okay. All right.
Yeah, so when you start the main program, the main program determines what the hash size is. Either it's 100 or it's, what the user specified on the command line. So that's available inside your main program. You need to pass it to hash init. And if you're asked to dump all the cells, you need to know, what that hash size is, so that you can have a loop that dumps everything. So yeah, that's totally fine to use. My comment in the assignment is, if you were to write all of your code in one big long file called, main.c, make sure your static is not, make sure your global is not global in your main program. Put it down in the section of your file where you're using your hash functions, where you're setting those up. I keep getting a floating point exception message when I declare the static int for hash size. That's very bizarre, because there should be no floating point anywhere in sight. Yeah, that's a confusing one for me.
Maybe if you don't set the value in the variable, it does that? Because I know that static wants a constant of some sort.
Yeah, I can't imagine why it would give you a floating point exception, though. Unless you're not giving it a value, and then your modulo function is trying to use a hash size of 0, and that would technically be like a divide by 0. So it may be that the hash size isn't getting set. And so in your hash function, I would say before you do the modulo operation, maybe throw in a print statement and just print out, what the value of whatever variable is that you're going to use for this. Print that out with a nice clear message first, just for debugging, and make sure it's actually the hash table size. And I'm going to make a guess that maybe it's a 0 at that point, and that's where you're getting the exception. But if that's not it, come by office hours and let's look at it. Because that sounds like an intriguing error. All right, anything else?
Just none.
All right, let's go on to tree traversal. So, yeah, go ahead.
Actually, one last thing.
Sure.
Wait. Actually, no, never mind.
Sure. So we started talking about binary search trees. And a binary search tree is like a plain old binary tree with an extra detail, which is if you look at any node in the tree, everything to the left is smaller, everything to the right is larger. And so here's this tree I keep drawing. And this is a nice example of a binary search tree. So any node that you look at, the 40 for example, everything here is less than 40, everything here is bigger than 40. If that's true at every node in the tree, then it's a binary search tree. And binary search trees are useful because, for one thing, they make it easy to search. So if I want to search for a value, I can ask first, is that value at the root of the tree? And if it is, I'm done, I found my number. But if it's not, I can now ask, is the number I'm looking for bigger or smaller than the root? If it's bigger than the root, all I have to do is search the right subtree, because I know it's going to be there if it's anywhere. And if the number I want is smaller than the root, all I have to search is the left subtree, because if my number is in this original tree, it's going to be to the left of the root. And so this lets us make this nice recursive function that we did on Monday, where we have basically a 4-line search function, without having to, you know, actually like move down and keep track of current node and all that kind of stuff. So the next question is traversal. And traversal, this is a common but fancy word for going through your data structure piece by piece and generally printing it out or doing something with it. So on the midterm exam, question 3, you were traversing a linked list and adding the values of positive nodes along the way. And if we want to print the contents of a tree, we can say we will traverse the tree and print out the data value of each node. And we looked at a recursive approach to printing a tree last week, but let me give you a slightly different recursive approach, and this is called LNR traversal. And this stands for left, node, right. And here's the idea. If you want to print out this binary tree with LNR traversal, first print out the left subtree, then print the root, then print the right subtree. So LNR refers to the fact that first we're going to print the left subtree, that's the L part, then we're going to print the root node, that's the N part, and then we're going to print the right subtree, that's the R part. And when I say print a subtree, what do I mean? I mean print it using LNR traversal. So we're going to print this tree by first printing the left subtree. And how do we print this left subtree, which is 20, 10, 30? Well, first we print the left subtree of that, which means print this tree containing a 10. Well, how do we print this using LNR? First we print the left subtree, which is null, there's nothing to print. Then we print the root node, which is 10, so we'll output a 10. And then we print the right subtree, which is null, there's nothing to print. So that concludes the LNR traversal of the left part of this tree. Now we print the root node, which is 20. And now we do an LNR traversal of the right subtree, which is 30. Well, how do we print this tree in LNR order? First we print the left subtree, which is null. Then we print the root data, which is 30. And then we print the right subtree, which is null. And we're done. We've printed this subtree containing 30 using LNR. And once we've done that, we've completed printing this subtree using LNR. We printed the left subtree, the root, and the right subtree. So we've got to kind of pop our mental stack now, right? What did we just finish? We printed this subtree using LNR. Well, we started this by saying, let's print this tree. And we've got to do three things. First, we've got to print the left subtree. Well, that's what we just did. Now we've got to print the root. That's a 40. And now the last part, we have to print the right subtree. And we do the same process. How do we print this tree? Well, first let's print the left subtree. Well, how do we do that? First print the left subtree of this, which is null, and then print the root, which is 50. And then print the right subtree, which is null, and we're done. We've printed the 50. And that was the first of 3 steps to print this tree. Print the left subtree. We just did that. Now we print the root node, which is 60. And now we print the right subtree using LNR. Well, how do we print this tree? First print the left subtree, which is null. Print the root node, which is 70. And then print the right subtree, which is also null. And that concludes printing this tree in LNR order. And that concludes printing this tree in LNR order, because we printed the left tree, the root node, and the right tree. And now that we finished printing this subtree, we're actually done printing this original tree, because what did we do? We printed the left subtree, that gave us this output. We printed the root node, which gave us this output. And then we printed the right subtree, which gave us this output. And we're done with our traversal. And miraculously, this LNR traversal not only printed each piece of data from this tree, it printed it in increasing order. And if you have a binary search tree with this property, things on the left are smaller than the root, things on the right are bigger, and you do an LNR traversal, your data comes out in order. And so this is sometimes called in order traversal. And it's probably the most common way we print trees, because a lot of times we want to get the data out in increasing order. And so if we want to write an algorithm to do this, well, here's an algorithm for left node right traversal given the root of a tree. And so I'm going to have, this base case. If the root is null, then just return. So if we're trying to print the left subtree of 10, which is null, we're just going to return. There's no need to do anything fancier than that. Otherwise, let's print out in left node right order the left subtree of our root. And then let's print the data of our root, and then let's do a left node right traversal of the right subtree. And that's your whole algorithm. Questions about this?
So in a binary search tree, you can't have duplicates, right?
You could. I'm not going to deal with duplicates, but I don't think they mess you up too badly. Well, they could mess you up badly. So yeah, we're just going to not deal with duplicates.
Okay.
I would say if you want to support duplicates, maybe you would do something like use a more complex node structure that would include how many times that value appears in the tree. So we've done left node right, which is in order. There's two other ways we can traverse a tree. The first is to do the root node first, and then the left, and then the right. And this is called pre-order. And the third approach is to traverse the left subtree, and then the right subtree, and then the root node. And this is called post-order. And there's cases where we'll do different kinds of traversal, but the algorithm is exactly the same, except if we want to do node left right, first we print the root node's data, then we do node left right on the left, and then we do node left right on the right. If we want to do post order, first we do left right node on the left, then we would do left right node on the right, and then we would print the root node data. And so it's really just changing where we print in this set of 3 steps. That's all you have to do to code different search orders. So one thing we can do with trees is we can take something like an arithmetic expression. So for example, suppose you want to do you know, a plus b times c plus d. So you want to add a and b, you want to add c and d, and then multiply the results. And you know, on a calculator, if you just say a plus b times c plus d, the multiplication gets done before the addition, right? There's a precedence. And in C, if I didn't have these parentheses, this would be a plus b times c plus d. And so these parentheses let us specify an ordering in which we want operations to happen. And we could represent this arithmetic expression with a binary tree. Now, it's not a binary search tree, but we could represent this information with a tree as follows. I could make A and B and put a little plus sign here. And I could take C and D and put a little plus sign here. And then I could put a star. And this tree basically represents the idea that our expression is the result of multiplying 2 things. This thing and that thing. Well, this thing is an arithmetic expression that's the result of adding 2 things, A and B. And this is an arithmetic expression that adds 2 things, C and D. Awesome, good deal. So this is a tree representation of this expression. And if you want to calculate this in a computer, you have to do some work, right? You need to see the parentheses and remember that you're inside parentheses and do your calculation until you get to the close paren, and then save this number somewhere. And there's a multiplication. Remember that, but here's parentheses. Start doing, you know, another sub calculation and so on. And then take those 2 things you remembered and remember the star and multiply them. But there's a really easy way, if you have an expression stored in this kind of tree, to actually calculate what the value of that expression is. And this is something called reverse Polish notation. And usually some people are familiar with this. It used to be that Hewlett-Packard calculators worked using reverse Polish notation. And if you had an HP calculator and somebody tried to borrow it and they didn't know this, they wouldn't be able to use it. Because on a regular calculator, you'd say parentheses, you know, 2 plus 3 close paren times parentheses 4 plus 5 close paren equals. And that's not how reverse Polish notation works. So in reverse Polish notation, what you would do is something like this. You'd say, here's A and B, I want to add those together. And then I have C and D, I want to add those together, and then I want to multiply the last 2 things that I calculated. So yeah, that's called reverse Polish notation.
That's weird.
Yeah, and it's you know, if you didn't have one of these calculators, it was just like your calculator's broken, man. But the cool kids had the HPs, right? Because this turns out to be a really comfortable way to do calculations, and you don't need parentheses. And it's used sometimes inside computers to do calculations, because if you write your expression like this and you do a left-right node traversal, you end up with the reverse Polish notation version of your original expression. So left-right node would say, let's first traverse the left subtree using left-right node. And so that means, you know, traverse the left subtree is A, right subtree is B, print the root node. So that's the LRN of this subtree. And then we have to do the right subtree in left-right node, which will be C, D plus. And then we print the root node, which is star. And bingo, there's our RPN expression. All right, so why is RPN interesting? So we talked about stacks a while ago. Let me go back to stacks for a minute and talk about how you can make a calculator using a stack. And let me plug some numbers in. Well, no, I can stick with A through D. So AB plus CD plus times. If you were given this expression and asked to calculate the value of it, it's really easy to do if you use a stack. And so here's how we can do this. So take successive tokens from the input string. In this case, my tokens are 1 characters, but you know, if this was a number, that would be a token. If this was a variable name, that would be a token. But we can just think of tokens as single characters in this simpler example. So take successive tokens from your input string. If it's an operand, push that onto the stack. If it's an operator, then we want to pop, operate, and push. If your stack is empty, then you're done. So what would this look like? Here's a stack. And I'll put my top of the stack, you know, towards the top of my page. So it's like a stack of plates or something. All right, I'm going to take my first token A, I'm going to put that on my stack. I'm going to take my second token B, I'm going to put that on my stack. I grab my third token plus, that's an operator. So what do? I pop off the B, I pop off the A, and I apply the operator plus. And then I push the result onto the stack. So now my stack contains whatever A plus B is. So I've chewed up 3 tokens. Now I grab my C token, I push that on the stack. I grab my D token, I push that on the stack. I grab the plus token, that's an operator. So I'm supposed to pop, so I pop off the D and I pop off the C, and I add them together, D plus C, and I push that onto my stack. So now my stack has D plus C. And now I get to my asterisk token, and that's also an operator. And so I pop off the D plus C, and I pop off the A plus B, and I apply the operator. So I multiply those, and I push the result onto my stack. So this will be, and I'll rearrange it, this will be A plus B times C plus D. So this ends when the string is empty, right? So if I've hit the end of the string, there's no more tokens, I'm done, and my answer is on the top of the stack. So how can we write a compiler that understands arithmetic expressions? Well, one way to do it would be, you know, if we've got a statement like, you know, x equals this stuff, go through this and build a binary tree by you know, parsing your input and building subtrees every time you have parentheses and so on. And then take that and do a left-right node traversal of it to get a string, and then run this little algorithm on the string using a stack to calculate values, save them on the stack, and when you reach the end of the string, your final value should be on the top of the stack. And you can do that as an interactive calculator, or you could translate that into code if you wanted to do this as part of a programming language, for example. So that's kind of a happy little application of different traversal orders for trees. So what do you think happens if you do a right node left traversal on a tree? What do you think you get out?
If you do what, sorry?
Right node left traversal.
Right node left traversal.
Instead of left node right.
I'm actually sorry, I didn't hear what either of them are, or how they traverse.
So traverse the right subtree, then print out the root node, then traverse the left subtree. Or what do you think the first thing will be that's printed if you do right node left on this tree?
50.
Oh, someone got it in chat, yeah. This will print out your data in descending order. Because first we print out everything in here, and then we print the root node, and then we print everything in there. And how do we print everything in here? First we print everything in here, and then the root node, and then everything in here. And so intuitively it feels like, you know, this is going to print 70, 60, 50. That'll be the right subtree. Then we'll print the root node, that's 40, and then we'll print the left subtree. And so, yeah, it's exactly right. It goes from 70, 60, 50 down to 10. So it prints it in descending order, whereas left node right prints it in ascending order.
I see. Okay.
So if you're in 215 this quarter, we're starting mathematical induction this afternoon, about 2 hours from now. And this is going to be very familiar to stuff that we're talking about here. For example, if you wanted to convince yourself that, you know, printing this out in right node left does print the numbers in decreasing order, right? Well, if you believe that that's what this does, then you can prove that that's what this does. If right node left always prints things in descending order, well, to print out the contents of this tree in right node left, first I'll print all of this stuff, which is bigger than the root, in descending order. So the top half of my numbers will definitely come out, you know, from largest to smallest. And then I'll print this number that's kind of in the middle. And then, you know, the last thing I'll do is traverse the left subtree, and if I believe right node left will print this in descending order, then the entire tree got printed in descending order. And so to prove that this works, all I need to know is that this works. and that's the magic of recursion, and that's the magic of mathematical induction. And the only reason that we know this works, the main reason we know this works, is this line right here. If the root is null, we're not going to print anything. And that's the correct way to print a tree that has no data. And it's really the fact that this statement makes this function do the right thing that makes the whole function behave correctly. So if you've already done 215, that's the basis case. That's the n equals 1 case. If you haven't done 215, we'll get into this. But you can come back to this in the back of your minds if you like. All right, let me do one or two more examples of functions we can use for working with trees, and then we'll start writing some code. So the next is the notion of height. And remember, we defined the height of a tree based on the depth of nodes. So if here's a tree, we can define the depth of each node as the number of steps from the root to that node. So this has a depth of 0. And if I've drawn this carefully enough, all of these nodes have a depth of 1. These nodes have a depth of 2, right? You have to go 2 hops to get to any of these. These have a depth of 3, and this has a depth of 4. And so the height of the entire tree is 4. Why? Because that's the depth of the deepest node. So the height is like the largest number of hops from the root to any node. In this case, it's 1, 2, 3, 4. So if you wanted to write a function to find the height of a tree, you could do it by doing some kind of algorithm to move from the root to every node and counting how many steps it takes, and remembering the largest number of steps, and at the end of all of that, whatever the largest number of steps was, that's the height. But we can also do this recursively. And we do it recursively with the following observation. This tree has 2 subtrees. One of them is over here on the left, one of them is over here on the right. If I were to find the height of each of these subtrees, this left subtree has a height of 1, because, you know, it's 1 hop from the root to the only node. This right subtree has a height of 1, 2, 3. The height of the tree is 1 more than the height of the highest subtree. It's 1 more because, you know, to get to the root of this subtree, I have to make 1 hop from the root of the original tree. And so the height of a tree equals 1 plus the largest of the height of the subtrees on the left and the subtrees on the right. Does that make sort of logical, intuitive sense? Can you see that visually?
Yeah, that makes sense.
Wherever that deepest node is, whatever its depth is in that subtree, its depth is going to be 1 more in the original tree because you have this extra hop from the root. And so we can actually use this recursive definition of height to make a function. So I can calculate the height of the left subtree and save that in a left. I can save the height of the right subtree. And then I can say if left is bigger than right, return 1 plus left. Otherwise, I can return 1 plus right. and I don't need an else in here, because if this is true, I'm going to return, I exit my function. So I can just, make a plain return statement here. And this almost works, but this will segfault. And it will segfault because when I try to figure out the height of this left subtree, first thing I'm going to do is try to figure out the height of the left subtree of this little tree, which will be just one node, which will ask me to figure out the height of the left subtree of this tree with a single node, which will be null. And when I try to find the height of a tree that's null, when I try to find null arrow left, I'm going to segfault. Right? That's our most common segfault, is trying to dereference null. But if my tree has no nodes, I don't need to do anything to find the height, because we have a convenient definition. If you have a null tree, the height is defined to be -1. And it's -1 because if you have a tree with just a single node, the height of that tree is 0. The number of steps from the root to any node is 0, because there is only one node and that's the root. So we define the height of a null tree to be -1, and so here's our base case. If the tree is null, return -1. And there's a fully working height function. And we're not explicitly doing any kind of traversal. We don't have, any node pointers that we're moving to node arrow left or node arrow right. We're not, implementing a stack and coming back and looping and all that kind of stuff. We're really just writing some C statements that capture this definition.
That returns -1?
That returns -1, yeah.
Interesting.
So we're saying if the left subtree is higher...
And remove the 1 plus left and 1 press right?
Sorry, say again?
Couldn't you, or return 0 or something like that, and then remove the 1 plus left and 1 plus right?
It's a good intuition, but if we always return the height of the left subtree or the right subtree, I think this function will always return 0. This is really the only thing that ever gets us a different height.
Oh, okay.
And that's a little weird to think about, at least for me at the moment. But if we were to do this in a loop, we would move from the root, go left or right to find a node, and each time that we move down, we would add 1 to a counter. So then when we got down here, we'd say, oh, the depth of this node is 4. Well, that incrementing is actually happening right here. And it doesn't look like we're counting nodes here. We're just adding 1. But because we're calling this function, that's where that repeated increment comes in. And if we call this function 4 times, we'll end up, incrementing by 4. All right, so this hopefully looks a little weird, right? But also hopefully kind of is somewhat believable. Let's do a 5-minute break, and we'll come back, and then let's start writing some code. We'll implement some trees by hand inside a C program, and we'll start doing some traversal and play around with it and get our hands dirty with it. So let's take a break. Let's come back at 11:10. All right, so I'll see you in a few minutes. All right, what we got in chat here? Yes, yes, good explanation on recursion. All right, so let's do some coding. And whatever we come up with today, I'll post this on the shared code area under some descriptive name like trees or something. All right, so let's define a tree node. And I'm just going to call this a node. And I'm going to define three pieces: a left, a data field, which is an integer, and a right. The order in which I do this is important. If I have another file with functions, and in that file I define a node with a different node order, all sorts of crazy things will happen. Because the fact that I'm listing, you know, left and then data and then right, the compiler uses that ordering when it decides where to store these things in memory. And if I have another file where I define these things to be like data left right, it may use a different ordering in memory. But when the code is running, you know, CPU memory hardware level, it has no way of knowing that, hey, this thing that I'm calling left here, this other function was calling that the data piece. And so always be careful of the order of these. And this is another reason why it's nice to put these kinds of declarations in an include file, like a .h file, so that every time that you want to declare the structure, you don't rewrite these statements, you just include that one .h file. Not going to be an issue here because we're just writing, you know, one big long main program here. Alright, so here's my root node. So this is the root of the tree. And let's get a little bit fancy here, right? I want to malloc a new node here, but I'm going to make a function called new node that will take care of the malloc for me. And so this is going to be something that returns a new node. So I'm going to malloc a size of struct node. And so I could get away with this as my new node function, right? It just does a malloc for enough bytes to store a node, saves the address that malloc returns in this variable, and then returns that variable. And then I can do something like root equals new node. All right, there's a few embellishments I'm going to want to make on this. So the first thing is make sure that you don't forget about null. When I create a new node, so here's my new node. I've got a pointer, a data field, and a pointer. And chances are, you know, I'm going to give my left and right pointers something to point to. But I may not, especially if I'm just creating the root and I have no children. I'm probably not going to do anything with those left and right fields, but don't just leave them unassigned. Any variable that you want to have a value, make sure you give it that value. And so I'm just going to do something for safety in here. Anytime I create a node, I'm going to explicitly define what the values of the left and right child pointers are. And so I'm going to say return value left equals return value right equals null. If I don't do that, I'm inviting at least warnings from Valgrind, but possibly on badly behaved systems, I'm inviting really bizarre behavior, because if those end up not being null, weird things will ensue.
What the heck is that?
What is what?
You did equal to right value equal to null. I've never seen that. That's
Oh yeah,
interesting.
that's legit in C. So you can do, you know, I equals J equals K equals 1. That'll initialize all of those to 1.
Really?
Yeah,
That's super cool. I didn't know that.
it's handy sometimes. Alright, the other thing is, usually when I create a node, I'm going to want to at least specify what the data value is. I don't usually just create a node because I'm you know, redecorating and I want some nodes scattered around, but I don't care what their value is. So I'm usually creating a node because I have a piece of data to store. And I'm going to make my new node function super duper fabulous, and I'm going to say, let's take an integer argument that I'll call data to save. And so I'll malloc my node, and then let's save the data value. So I'll say return value data equals data to save, and then I'll go ahead and set the children to be null. So now I'm going to prototype my function. And now when I say new node, we'll make a node with a value. Let's you know, pick on our or my favorite tree. Let's make a node with a root value of 40, because this one's probably familiar to us. So I'll do root equals new node 40. And that's going to be my whole program for now. It's going to be very, very exciting. So struct node root will be new node 40. That should create this tree. Just a 40 in it. So we can compile that, we can run it, nothing blows up, but nothing exciting happens. Let's debug it. So we're about to call new node. I'm going to say next, which says run the new node function, and then come back in here. So this will take me to line 16. And I can print the root, and root is, you know, some number that we may recognize as being, you know, in the heap area, so it's something that was malloced. And I can say print root arrow data, and it's a 40. I can print root arrow left, and it's a 0, which is null, and I can print root arrow right, and that's a 0, which is null. So this code has apparently succeeded in creating the root node of a tree containing a single node, which is the root, with a value of 40. Alright, let's make our tree a little interesting. A little more interesting. Let's put a 20 here on the left. So how could I pin a 20 to be the left child of my root node? What could I type? I'll go back in a second. I lost my chat window.
I don't know, 40 or root dash left equals new node 20 or something?
You got it. That's all it takes. right? Root is...
Whatever it takes.
Say again?
Oh, sorry, never mind.
Okay. Yeah, so root is pointing to... root is pointing to a node, right? Root arrow left says go to that node and pick out the left field. That's this field right here. And I'm setting that equal to the return from this function code. Well, this function returns a pointer to a node. And so this statement, root arrow left equals new node 20, is making this left field point to another node, which is going to contain a null, a 20, and a null. And if I want to put a 60 over here on the right, I can do the same thing. And this should give us a tree containing 3 nodes set up in this organization. Man, I keep closing my Zoom windows. That's a drag.
My question is, if you were to have, say a fat array of all this data, or, or you were to pull it out of a file or whatnot, how would you know? You just have to, find the middle of it or something? Or sort it by low to high and then find the middle to create the first node? Or...
So in reality, to build a tree, we're just going to build it piece by piece as the data comes to us. So if we were given our data in the order 40, 20, 60, this is what we would end up with. If we were given our data in the order 20, 40, 60, this is actually what we would end up with. We get a really lopsided tree.
Oh, right. I see. Okay.
But eventually we're going to talk about how to take this and turn it into that so that it's not lopsided. That's a concept we call balance, and it's going to take us into something called AVL trees. That's probably at least a week away, and that's the most sophisticated thing we're going to do with trees is rebalancing them to make them nice and fluffy and full. But for now, we're just coming in from outside and just cobbling this tree together by hand, just to play with it. So let's compile this. Let's run it. I'll start. So I'll create the root. I'll add the left node. I'll add the right node. So now if I look at my root, it's some location in memory. If I look at what root actually looks like, it's got a data value of 40, a left and a right child, as so. If I print root arrow left, right, that's the location of the left subtree. If I print root arrow left at data, that's our 20. That's coming from right there. And if I print root arrow right arrow data, that's our 60. If I print root arrow left, that's going to be null. Because our left subtree has nothing to the left. There is a left pointer, but it's pointing to null, which is why we're not drawing anything on the picture. But root arrow left is null, so is root left right, and so on and so forth. Now, just for kicks, we can look at this stuff in memory. And we don't usually have to do this for trees, but for other structures we may have to. But let's look at the root again. It's this location in memory. So if we examine that location with an X, what do we find? We find 55, 75, 62, 80, followed by 55, 55, followed by 28, followed by a 0, followed by 55, 75, 62, a 0, followed by 55, 55. This is the root. It's 6 fields, 4 bytes each, 24 bytes total. This is the most significant part of a 48-bit memory address or a 64-bit memory address, which corresponds to left. 5555, 5575, 6280, that's the address of the root's left child. That's what we saw up here. So the first 8 bytes in memory where the root is stored code the address of the left child. The next 4 bytes code the root node's data. Well, 28 hex, that's 2 times 16 is 32, plus 8 is 40, that's the data. The next 4 bytes are padding, so that's that blank space that we've seen compilers put in sometimes. And then the next 8 bytes together code a 64-bit number, 5555 blah blah blah, 62A0, that's the address of the right child. And if we examine, say, that right child address, what do we see? We see a null. It's a 64-bit 0. That's the address of the left child. We see the right child's data, 3C. 3 times 16 is 48, plus C is 12. 48 plus 12 is 60. That's the right child's data. And then the right child is another 64-bit 0. That's null. So by just looking in the memory itself, you can figure out what this data structure looks like. But that's a hard way to do it. Sometimes you're going to have to do that. But since we compiled with GDB, we can do things like, you know, print root arrow right and see, you know, what the fields are from that, or what the address of root arrow right is, and so on. So take advantage of the fact, if you compile with -G, that you can use the symbolic names, you can dereference pointers with arrows and so on and so forth. But if you have to, you can always go back to just the bare memory map and look at that. And sometimes it means looking at this, right? And this is a memory dump, and sometimes, you know, a program will segfault, and before it exits, it will dump the contents of an area of memory into a file, and you can go back into the file and look at it like this and piece together, oh, this looks like an address on the stack, this is a data value, this is an address, okay, this is a node. And you can kind of reverse engineer what the state of the system was. And that's actually pretty fun to do, if you like things like that. All right, so we've got a tree with 3 nodes. Let's add some more stuff. Let's put a 10 over here. So the 10 will be to the left of the 20. And I can write some slightly horrifying code like this. So if I say root arrow left arrow right, that's root arrow left is this node, arrow right. There's my 30. And I'll do a few more statements. Root arrow right, arrow left is 50. Root right, right is 70. So that's putting my 50 down here and my 70 over here. So I'm building a tree the hard way, right? By just creating 7 nodes and putting them, you know, in the right place relative to other nodes. But when we're developing code, when we're doing basic debugging, especially before we've written an add function or an insert function, this is, you know, a perfectly legitimate way to get yourself some test data. So let's print the contents of the tree in left node right order. There we go. We're done. All right, got to do some more work.
You forgot the little arrow thingy on the
I did.
board.
Thank you. All right, so let's prototype our function. And so we're going to do this in order traversal, left node, right. So this takes a struct node root. All right, well, we talked through an algorithm for doing this that's recursive, right? Basically, traverse the left subtree, print the root node's data, traverse the right subtree. With this extra catch of make sure if the root's null, we don't try to print null's left subtree, because that's going to blow up. But that's our basic algorithm, right? And so we can translate that into code. Print root arrow left. Right, so these functions print, these are, calls to this function that we're defining right now. Printf is just our, CSE222 print function. It's a built-in function that, will take this number and print it out next to the word data equals. But this and this, these are recursive calls. And then we need this one extra check in here, make sure if the root's null, we don't try to do anything too bizarre. So if the root's null, there's nothing to print, we're just going to return. All right, everybody see what we're trying to do?
We need the curly brackets.
Curly brackets on
the one-line if statement.
yeah, so normally I'm religious about putting in curly brackets, unless it's a really short statement I want to do and I only want to do one thing, and then I'll leave them off sometimes. But that's only the past year I've been doing that. But yeah, for a one line you can get away with that.
I think it's considered bad practice for some cases. I know at work all our linters will scream at us if I try to do one-liners like that.
If you do this, oh, interesting. Yeah, so
PHP.
So until about a year ago, right, I would have written this. And I don't know, maybe it's COVID, maybe it's made me like more carefree in some weird way. But about a year ago, I started, feeling comfortable doing this. And I don't know why. It's just something I observed in my coding. My argument in favor of doing this, though, is, sometimes you're writing code and you want to say, ready to return, right? You put in a debug statement, right? Well, if I forget if I don't have brackets originally, and then I try to add this statement, this is not going to do what I want. It's going to say ready to return if root is null, but then it's going to return regardless of whether this is true or not, because this statement is only, it only goes along with that if statement. This does not go with the if. It's a separate statement. And having those curly brackets makes it less likely that you're going to do this by mistake. But like I say, I've changed my ways in the past year, so this is legit. But some places don't like it, I guess. All right, so if the root's null, we're going to return. Otherwise, we're going to, you know, do our recursive thing. Use our function to print the left subtree, then print the root data, then use our function to print the right subtree. And so this one call should print out our tree data in increasing order. So there you go. And this is a lot less code than trying to move down the tree and keep track of where you are and do this thing that I'm doing where I say, okay, first we're going to do this, so that means first we're going to do this, and then do that, and then come back and do that. Right? Every time that I move my hands, I need to save some information somewhere. I need to know, okay, my hand is covering this up, and now I'm printing this, and now I'm covering this up, and I'm printing this. And when I'm done with that, I need to uncover this and print the root. All of that is asking you to remember state information, right? Where you are in the process of applying this left node right algorithm. That all gets managed for us by making these calls to ourselves. And the reason this works is because in most languages, when you call a function, all of your current local variables are saved. They're saved on the stack. And root, for example, is a local variable. I can change the value of root in here and it has no effect, you know, when I exit the function. But if I'm making a call to any function, whether it's myself or some other function, the current value of this variable is saved. It's tucked away on the stack, right? That's my hand, you know, covering this up and saying, let's go down here. Well, it's remembering my hand covered this up. And when you return from a function call, those variables are restored. And so this prints the left tree, and then the data, and then the right tree. But when we make this call to print root arrow left, we have a new, what we can call a call frame, a new instance of this function. And in that instance of the function, root is, you know, the left subtree of the previous root. So if we call print on this tree containing 7 nodes, the first thing it does is print root arrow left. So we make a call to print, and in that instance of the call, root is the 20. And we'll do all the stuff to print this. And when we return from that function call, when we come back, root is again the original root of the original tree. It's the 40. And so when we print root arrow data, it prints out the 40. And then when we call print on root arrow right, it's the right child of that original root. So we're calling print on this thing. So someone said recursion reminds me of recursion, which I think is true. And then someone posted a link.
I don't even know if Google searches work like that, if you could just post a link like that. Like
Apparently you can.
Really? Did
Yeah.
it give you the recursion? Did you mean recursion?
Right? No, it did. Oh, yeah, yeah. It did. All right, so you search for recursion. Cool. That's cute.
Google's pretty funny sometimes.
I know, right?
You know there's definitely some high-level nerds.
Oh, yeah. Absolutely. A couple of years ago, around the beginning of COVID, actually, I was prepping for a lecture, and it was a 215 lecture, and I normally write some code in there, and I do it in C, and the C code gets confusing, so I thought I would do it in Python. And I'm not very familiar with Python, so I was Googling some syntax question, and this weird thing happened. My browser window, like, changed color or something, and the banner at the top that says Google looked like it flipped in 3D and tilted towards me, and there was like a little black spot inside, like a secret compartment where you could hide things. And then these words came out of it, and it said, "Looks like you're speaking our language. Want to take a test?" And I had stumbled across this thing that Google does, where they analyze search patterns and things that people are looking for, and if you hit this trigger, they think, hey, maybe this person is into programming. Maybe they'd be, someone that would be fun to hire at Google. And so it took me to a page, and I, snooped around and stuff, and you find a README file, and you start looking. Anyway, there's these programming challenges, and there's a storyline about, these little creatures who are trying to like save the galaxy, and they're under attack, and you have to like write code to do certain things to help them in their quest for freedom. And it was really fun. And there's like several levels of challenge, and when you get through like the fourth level, it invites you to put in contact information and have someone contact you. So I did that, and a recruiter from Google called me up, and we talked and that kind of stuff. So Google is like really really interesting. I mean, they understand technology like a lot of other tech companies don't seem to. A lot of companies do tech, and they sell tech, and they've done it for a long time, but it feels like they don't really get it. People like, augmented reality, let's do AR, But Google, I've got to say, for everything else, they seem to really understand the potential of technology and ways to use it and so on. And
did you get a job there, or were you already fine?
I did not. So it was right in the beginning of COVID, and I basically pitched a moonshot project to them, and something may come of it somewhere down the road. But things were like transitioning to online for them, and there was lots of uncertainty about the economy and so on. So we kind of left it with a let's keep in touch, and
would that be someplace that you'd be willing to work?
If they wanted to hire me on the terms I was proposing, yeah, definitely. But it's like a moonshot kind of endeavor. It's like, let's take a huge amount of money and throw it into this really high risk project and hire a bunch of people and see if we can change the world, And not too many places are like that. The places that are into that kind of mindset don't have a lot of money, and the places with a lot of money tend to be pretty conservative with what they want to fund. So, been looking for a sweet spot for a few decades, like 4 decades.
That's super cool, though.
Yeah. Google's neat. So if you ever get that on your browser, follow through with it, because it's fun. And they let you work in Python or Java, when I did it at least, so it's good stuff. All right, so tree code, right? So this is our first, recursive tree function, and it's this easy, right? Now, if we forget to check the base case, if we don't do this, and we run it, we get a seg fault. And what happened was, we went down the tree until we got to, where we were trying to traverse a tree containing just one node, a root. And we said, let's print out the left subtree. Well, the root's left subtree is null, so we called traverse with root being null. And then when we said, let's go ahead and print out that null tree's left child, that gave us a seg fault, because you can't dereference null. And it's interesting that, we never printed anything even though we moved down the tree. Now, if we do this in a slightly different order, if we do this in pre-order, so now we're saying let's print the root node and then traverse the left tree and traverse the right tree. Well, now we'll get something slightly more interesting, which is we printed out the 40, so we started to traverse the entire tree. And then we printed a 20 because we started to traverse this tree. And then we printed a 10 because we started to traverse the left subtree. To traverse this node, first we said print out the 10, and then let's traverse the left subtree. So after we printed the 10, we tried to traverse null. And in this case, when we tried to print null arrow data, that's when we got the seg fault. So I'll leave this with in order traversal, because that's what we said we were going to do. And I'm going to post this code. So questions about this?
Statement commented?
Sorry? Oh, let me uncomment this, yeah.
So to just switch that from L and R to RL, R and L, you would just change the locations of root dash left and root dash right?
Yeah, so if I print out right and then node and then left, that gives me my data in descending order.
Oh, wow, that's super easy.
Yeah.
What happens if you do node first?
So if you do node left right, you get a very strange order. So 40, 20, 10, 30, 60, 50, 70. And these are usually pretty confusing to try to do by hand, but if we're doing node left right, we're printing out the 40, and then we come down here and we print the 20, and then we go to the left and print the 10, and then we go to the right and print the 30. And now we've done the node and the left, so we come over here and we're going to print this subtree. So we'll do the node, and then we'll come down and do the left, and then we'll go and do the right. So 40, 20, 10, 30, 60, 50, 70. 40, 20, 10, 30, 60, 50, 70. And just for kicks, we can do left, right, node. And there's nothing obvious about that. 10, 30, 20, 50, 70, 60, 40. It's not like just a reversal of this or something.
Interesting.
All right. All right. So so searching we've talked about previously. If you want to search the tree, all you have to do is check the root. If your data is not at the root, check the left subtree or the right subtree. And for a BST, right, we don't have to check both. If our number we're searching for is bigger than the root, just check the right subtree. If it's smaller than the root, just check the left subtree. So we could code a recursive search function, but we did some pseudocode last time. I don't want to give you all of the code for PA4. So we're not going to code that. But let's talk.
PA4 is a search tree.
Say again?
PA4 is a search tree.
PA4 is going to be a whole package of tree functions, including search.
Sorry, I meant binary tree.
Yeah, yeah. But let's talk about adding to a tree. So I've mentioned that to add to a tree, we can use our search algorithm, where we start from the root and we move left or right. And so let's suppose, 40, 20, 60, and let's add a 10. And so do what you would do if you were searching for a 10. Start at the 40. 10 is smaller, let's go to the left. 10 is smaller, let's go to the left. There's nothing to the left. Let's put our 10 right there. If you want to add a 50, start at the root. 50 is bigger, so go to the right. There's a 60. 50 is smaller, go to the left. There's nothing to the left. Go ahead and add a 50 right there. And so if we think in terms of starting from the root and just moving left right in a search algorithm, when we get to a spot where we find an empty child, that's where we put the thing that we're adding. And so that's not too bad to code. You need a temporary pointer, you initialize it to root, and you just change it to the left or right subchild until the thing you're going to change it to is null, and then you make a new node and you tack it on there. But again, there is a recursive way that we can think of adding to a tree. So how do we add to a tree with a given root? So let's do root comma data. If data is less than the root data, well, we know that our data should go somewhere to the left of the root. And to the left of the root, we find a binary tree. All we have to do is add our data to this binary tree. How do we do that? Well, let's just use our add function. Otherwise, let's add our data to the right subtree. And this does not work the way it's written, but this is the spirit of what we're after.
And then you need to have a beginning if statement to just actually add it there or something.
Yeah, there's nothing in here that actually changes the tree. And so that's a hint that we're missing something. And we don't have a base case, and we usually have a base case, so that's another hint that we're maybe missing something. But the spirit of this is correct, right? If you want to add data to this tree, just see which subtree it should go to and use your add function. Right? So that's gets you into the recursion club. But this will not do anything except, blow up eventually in segfault. But if we are a little more careful with this, we can make this a workable function. So let me do this with code. So a function to add a node to a tree. And the trick here is I'm going to have my add function return a struct node pointer. Alright, this is going to return a pointer to a struct node. And the reason I need to do that is imagine I'm beginning with an empty tree. An empty tree is null. And if I were to say, add null, comma 40, I can't just call this function and magically create a tree containing a 40. I mean, maybe I do, but how am I going to get to that? Right? Maybe it'll build a tree somewhere in memory, but unless I have a way to get a hold of that, this does me no good for building up a tree. So I'm going to call my add function by saying something like root equals add. And I'm going to pass it the current root of the tree and the thing I want to add to it. and I'm going to initialize this whole thing by setting root equal to null. So there's two things here, right? The first is when I call my add function, in addition to passing the root of the tree I'm adding to and the value I'm adding, I'm going to set my local copy of the root to whatever the add function returns. And I'm going to make sure I initialize that to null to say, hey, I'm starting with an empty tree. Alright, so my add function is going to return a root. And if the root of my tree changes, as it does when I go from an empty tree to a non-empty tree, I'll return that root in either case. But in that case, the root will be a new root. Otherwise, it'll just be the old root. All right, so I have an edge case here. So if the root is null, I'm going to call my new node function to create a new node, and I'm going to return that. Otherwise, I'm going to see if my data is less than root arrow data. So if the data I'm adding is smaller than the root, what do I want to do? I want to add to the left. So let's say I want to add a 25. Alright, I'm going to check my root. It's not null, so I'm not going to make a new root. 25 is smaller than 40. I'm going to add to this left subtree. And so I'm going to do that by saying call add root arrow left comma data.
So, what if root arrow left doesn't exist?
So there's the edge case. If root arrow left does not exist, then this will create a new node with my data, but I'm not attaching to it. It's created in memory, but I have no access to it. So in addition to saying, hey, 25 is smaller than 40, I'm going to add it to this left subtree, my add function will give me back the root of this subtree. I'm going to make sure that my root points to that on the left. And so I'm going to add one more thing to this statement, which is root arrow left. Equals the result of add. So I'm going to add to the right subtree and point to that on the left. And this is where all the magic happens. And when you make peace with this, I'd say you've probably got a really good handle on trees. Right? This is the kind of thing we're going to write for most of the really gory tree functions that we get into. So there's two things happening here. I'm calling the add function to add my data to the left subtree. And then I'm making sure that my current tree points to whatever the tree is that results from adding that data to the left subtree. And this only has an effect when my left subtree was null. If there's nothing on my left, this will create a new node, and this will set my left child to be, instead of null, to be that new node that was created. But if my left subtree looks like this and I add, a 25, the 25 will come over here, and my left child already was pointing to this root. It's not going to change anything. But if you don't do that assignment, everything breaks. Alright, and then I'm going to return the root of the tree. Otherwise, I'm going to add to the right. So root arrow right equals add root arrow right, comma data, and return the root. And so there's our add function. All right, do we believe this will work? I don't know. So let's comment all of this stuff out. Let's make sure, you know, there's nothing in our tree right now, and let's use our add function. Alright, so I'm going to start off with root equal to null. Alright, so start shouting out some favorite numbers.
20. 42.
Excellent.
3. Little large count. 6,742.
Got two numbers there.
7.
Keep going.
711. 263.
Alright,
Negative 15. Just
excellent. Yeah, I gotta have some negative numbers. Let's put a 0 in there too, just for kicks.
2I.
I'll just do 2. I is funny because it's not comparable to floating point numbers. Alright, so let's go with this. So I'm going to substitute a space with a new line everywhere on this line. So I'm going to break these out. And I'm going to insert add root comma. Actually, I'm going to insert root equals add root comma. I'm going to put that on every line. And I'm going to put my closing parentheses. Alright. Hopefully I didn't make any typos there. Even minus I pi. Good. Excellent. We'll put that in there also. Alright, so we're adding a bunch of stuff to our tree, and then we're going to print it out. And let's see if it blows up fabulously, or if it actually prints things in sorted order. I don't remember all these numbers, but we'll see if it compiles first of all. Good, I didn't make a mistake in there. Let's go ahead and run it. There's our data. And we have a funny 42 and 20 in there. So let's go back to left node right order. And let's run it. And there's our sorted data, smallest to largest. So we have a binary search tree, and we've apparently inserted the data in the correct way.
That's a super easy way to sort data.
Yeah, it is. And it's a very efficient way to sort data, actually.
That would have been so much easier on PA1.
Yeah.
Dang it.
So this is a powerhouse of a function, and it's not all that much stuff going on in here. There's no looping, There's no overt looping in here. There's no while loops or for loops. There's no temporary node pointers. It's really just, you know, let's add this to the left tree or add it to the right tree, or if there's nothing in the tree, let's just make a new node. But because of the way we're linking these things together, because we're taking the result of this and using that to change or specify the left or right child, this actually builds a binary tree. And there's our sorted data. Now what does this tree look like? Well, we can do the non-recursive version. So recursion is hard by hand, by the way. And it's fun to try to follow these kind of recursive functions on paper, but it's pretty tricky. It's not something that our minds find particularly easy or pleasant usually. But we can figure out what our tree looks like by doing the non-recursive version of adding nodes to our data. So let's bring this in here and let's build a tree. So we're starting with a null tree. We're adding a 20, and so 20 is going to be the new root. And then we're going to add a 42, that'll go to the right. We're going to add a 3, that'll go to the left. We'll add 677422, that goes to the right. When we add 6742, we're going to start here, go to the right, go to the right, go to the left. So this will be 6742. And then we're going to add 870,000, so we'll go right, right, right. This will be 870,006. And then 7 will come here to the left and will come to the right. 711 is bigger than 20. 42, it's smaller than this, it's smaller than this. So there's your 711. 11 is smaller, bigger, bigger than 7, so it goes there, and so on. And so you can cobble together by hand a picture of what this tree looks like. Yeah, I should have done 6 skrillion. And it's not going to be, you know, a nice symmetric tree where, you know, there's 1 node and 2 and 4 and 8 and 16 and so on. Chances are it's going to be kind of all over the place, right? And I can finish this up pretty easily, I think. So there's minus
So,
15.
balance this, would you just like print it out basically and then store that all onto maybe an array or something and then take the middle value?
So balancing is going to be a whole big long discussion. But the key to balancing is going to be to try to keep our tree balanced as we add things. And once you have a tree like this, it's really hard to balance. But if you have a tree that starts off balanced and you add one thing that makes it unbalanced, we can correct that pretty easily. And so the procedure will be, you know, if we start with a 10, 20, 30, we get a 10, it looks like this. When we add a 20, it looks like this. When we get a 30, it looks like this. We're going to notice that that's unbalanced, and we're going to do what's called a rotation and change this into this. And that'll be balanced. And we're probably, like I say, a week away from getting into that. But it's a process we do as we add to the tree. So this is what this tree happens to look like. These were random numbers that people shouted out. So it's you know, not the most balanced tree. Over here we only go down 3 levels. Over here we go down 1, 2, 3, 4, 5 levels, right? So it's a little heavy on the right side maybe. But, you know, it's still a binary search tree, and we can still print the contents of that. I think Surfpunk's dictionary defined a skrillion as 1 followed by a bunch of zeros. That was in their Surf's Up album, I think, in the liner notes. All right, so there's some recursive code. There's some details on how to add things to it and so on. So let's talk a little more about balance next time, and we won't talk about how to balance a tree, but I want to talk about how to define balance and how to measure it, and that's another really nice recursive function. And then I want to talk about tree traversal using a stack instead of doing it recursively. And this will be another good application of stacks to go through and try to print this in left node right order. And then we'll see what happens when we try to print this tree using the same kind of algorithm, but we use a queue instead of a stack. And these will both be pieces that we'll want for PA4. And then we're going to tackle deletion. And deletion is more complex than adding or printing. But we'll spend some more time playing with this, getting more comfortable with the ideas, and then we'll go ahead and we'll talk about deletion. And then we might go on from there and talk about how to balance trees. Or we may go on to something else and come back to that. We'll see. All right, I'm out of here for now. I'll see you in 2:15 if you're in there. I'll see you in about an hour. Otherwise, have a great time. Finish up PA3. Come by office hours if you want. Have a great weekend. I'll see you next time. All right, thank you.
See you in an hour.
See ya.